Hey guys, tonight we're going to talk about Hess's Law. We talked in the last section about calorimetry and how we could use that to calculate heat or to calculate enthalpy. But in reality, usually the way that we calculate enthalpy, if we're not in a lab setting, if we're working on a problem, is we use either Hess's Law or what we'll talk about in the next video, which is standard enthalpies of formation. So let's talk a little bit about what Hess's Law is. If you remember, a couple of videos ago, we talked about the fact that enthalpy is a state function, which means it doesn't really matter how we get there. It doesn't matter if we got there in 50 steps or if we got there in 2 steps. All that matters to us is what's the situation at the end. And so that allows us, that pretty much directly applies and ties us into what Hess's Law says. And so you guys can read through that just as well as I can, but essentially it just means that if we've got a bunch of steps, if we add the enthalpies of all those steps together to get our final reaction, then we can just add the enthalpies up as well to get our final enthalpy. And what you'll see is there's some similarities in doing this and in doing half reactions, and then we're going to have a couple of reactions that we're going to manipulate, and then we're going to add them together. The only difference here is at the end, instead of just getting a reaction like we did with redox half reactions, we're going to get a number on the side that's the result of some math that we did. And the math, of course, is super easy because we're basically just adding and subtracting. So let's just dive right in and work some examples. That's really the best way to sort of understand what's going on here. Let's say we take a case where we're trying to figure out what is the enthalpy for the combustion of methane. Okay? Specifically, what we want is the combustion of methane resulting in liquid water. Okay, so that's going to be a little bit different than if we get gaseous water, and we're going to see that here in just a second. So this is the equation that I'm shooting for. And so I'm going to sort of put that off to the side here because I don't want you to get confused by it. But this is my end goal. Like in a redox reaction, you didn't really know what you were looking for other than a balanced reaction. We know at the beginning of each one of these reactions what I'm looking for. So here's how we get there. We look up, or it's given to us in the problem, the reactions that make up the steps that will lead us to this. And so we've got one reaction here, and if you look at this blue reaction, that looks almost exactly like our original, except that you'll notice that the water is in gas phase. It says water vapor. And so we've got this whole complete reaction with an enthalpy, and it's almost our reaction, except that we've got something in the wrong phase. And if you recall, we said before that phases really do matter here. They matter a lot in the case of enthalpy because what's the difference between phases? Well, obviously, it's the kinetic energy in the system. It's the kinetic energy of the molecules, and so it matters what phase it's in. So we're going to need to add this red equation to it. So we've got gas phase water here and liquid phase water here. And so what this is going to allow us to do is that this essentially is 2 parts. So let's say we did a combustion and we got this and we got gas phase water, and then we had to do a second reaction to go from gas phase water to liquid water. That, by the way, is not actually the case. We don't have to go through, we wouldn't like individually do those reactions necessarily. This is just a convention to allow us to add everything up to get to our enthalpies. So we're going to add these up pretty much just like we did with redox reactions. So I'm going to draw my little bar here, and I'm going to, if you want to, you can put your little plus sign there, or a crazy crooked plus sign. That's what happens when you draw with the mouse. And then we're just going to add everything together. And the same things that were true in redox reactions, half reactions, are going to be true here. So if I have something that is the same on both sides of the equation, which of course I do, right? Okay, my gas phase water is the same, then I'm going to cancel it out or cancel as many as I can. Since I have 2 of each of these, I'm going to cross that out. And then I'm just going to add up everything to get my final result. So I've got 1 methane, 2 gas phase oxygens, 1 carbon dioxide, and 2 liquid phase water. So what I'm going to do is, instead of me writing this all down and making it sloppy, I'm just going to drag it down here. Okay, so that is the reaction that I was looking for, right? That is exactly what I wanted. And so now, here's the real crux of the matter. Here's what really matters for us is, how do I find this enthalpy? Well, it's pretty easy because I'm just going to take all of the enthalpies, and by convention, they're pretty much always written off to the side, and I'm just going to add them up, signs and all. And so if I add negative 802 to negative 88, then what I'm going to get is negative 890 kilojoules, and that's going to be my enthalpy. Okay, or my change in enthalpy, rather. Pretty simple. I mean, the math that we do in chemistry doesn't really get a whole lot easier than that. Now, of course, you're thinking to yourself, listen, Arnold, I know it can't be quite that easy. But really, it pretty much is that easy. The only thing that's different is that sometimes we have to manipulate these equations. That shouldn't shock you much. We manipulated them in redox. Sometimes we multiplied them by things. We added stuff to them and all that stuff. We're going to do similar things here in Hess's law. So let's work a slightly more complicated one. Enthalpy of reaction for the combustion of carbon to carbon dioxide is given here, negative 393.5. Enthalpy for the combustion of carbon monoxide to carbon dioxide is negative 283. And then it says, using this data, calculate the enthalpy for the combustion of carbon to carbon monoxide. Okay, so in other words, I'm trying to get to, hold on here guys, I'm trying to get to this, and I'm starting with this, but I'm going to obviously take some intermediate steps here because I've got some other information. So real quick, let's write down then like all of this information that's here in the problem. What does that mean for us in terms of reactions? Well, this first one, combustion of carbon to carbon dioxide, that's this, carbon, solid phase, okay, pretty much always going to be solid phase. We could theoretically have liquid or gaseous carbon, but pretty darn unlikely. So solid phase carbon plus oxygen, okay, it's a combustion reaction, right, so we know there's oxygen in it, is going to yield for us carbon dioxide, okay. We already know the enthalpy. It was given to us in the problem. You'll notice that I gave it a sub 1 here. That's just because I'm going to have a couple of things here, and so it's an easy way to sort of keep them separate. You don't have to do that necessarily. Carbon monoxide to carbon dioxide, that gives us a second one. So carbon monoxide to carbon dioxide is going to give us negative 283.0 kilojoules. Now, some of you may be freaking the heck out because I didn't use a whole number here in front of this oxygen. The reason I didn't is because what's given to me in the problem is kilojoules per mole of CO, so I have to keep this at 1 mole of CO, at least when I initially write it out. And the only way I can get the stuff to balance then is if I put 1/2 mole of O2 there. You might be thinking to yourself, why couldn't you just put O? Well, because it's not O, right? It doesn't exist as O, it exists as O2, and so I've got a 1/2 mole. Remember, a 1/2 mole, it's not like it's a half molecule. It's 1/2 a mole. It's half of Avogadro's number of them. So there's still plenty of them there. We can divide that by half. I know that might freak you out a little bit, but that's okay. So that gives us our second equation. Now, what you'll notice here is that if I just left this the way it was and tried to add stuff up here, it's not going to equal the equation that I want at the end. So, I mean, first off, what is the equation that I want at the end? Well, I want carbon to carbon monoxide, right? How do I know that? Because that's what it says here in the problem, carbon to carbon monoxide. Okay, again, you'll note that I've got this 1/2 mole of oxygen here. Don't freak out, okay? It's okay to have that. Again, it's because I want it per mole. And so if I got 1 mole of carbon here, that's the way it's going to balance. It'll be all right, okay? So what do I have to do manipulation-wise? Well, obviously, I want to get rid of these CO2s, right? And the way that I'm going to get rid of them is that I need to move one of them to the left-hand side, right? Well, I can't just move one of them to the left-hand side. What you actually have to do is you're going to reverse the reaction. Okay, so I need to pick which one of them I want to do that to, and I'm going to reverse the reaction. Well, in this case, I know that I want to end up with a product of carbon monoxide, and over here it's a reactant. So what I'm going to do is I'm going to rewrite this second reaction, okay, this red one here. I'm going to rewrite it essentially backwards. So I'm going to put CO2, okay, gas phase, yields carbon monoxide, again gas phase, plus 1/2, I know, it'll be alright, O2 in gas phase, okay? And so that's essentially my new reaction. So what do I do with the old reaction? Well, as soon as you reverse it, do yourself a favor, cross the old one out so that you don't get confused and try to add it up again. Now, what does that do to the enthalpy? Well, if you remember back when we did enthalpy and introduced it, and we said there were some quick hits at the end, and we said, hey, these are some things you want to do. If we reverse the reaction, then what we do is we reverse the sign of the enthalpy. So what was a negative 283 now becomes a positive 283. Okay? That's pretty much it as far as our manipulation. I mean, that's really all we need to do at this point. So I'm going to say, boom. I'm going to put my little addition bar there. I'm going to put my, as usual, crooked plus sign there. And I'm going to add everything together. Well, does this add up to what we want? Well, let's look at it. So CO2 is gas phase. There's one of them on each side. They're going to cancel, right? Boom. And so that leaves me with my carbon. Bring that down. And then my oxygen is the weird case, right? Because I've got a whole O2 over here, and I've got a half over here. We would cancel it out. And so this half gets canceled, and it leaves this one then as a half, which is what we want, right? That's what I've got down here. And then my carbon monoxide, we bring that down, and so everything's okay. And so now, all I've got to do at this point is just the math, right? Okay, so negative 393 plus 283. And so we're going to just punch that math out real quick, and that math is going to give us a delta H of negative 110.5 kilojoules. Okay, and really per mole we could say of carbon, right? Because we got 1 mole here. I mean, theoretically we could have messed all the balancing up, but then we would have had to manipulate more stuff up here. Okay, so it was a slightly more complex one, right? And I apologize that I'm going to make the video a little bit longer, but I want to go ahead and squeeze in a slightly more complex reaction. So far all we've done is 2 reactions. We could actually do 3 as well. And what I'm going to do here is, instead of belaboring the point, I'm going to do exactly the same thing I did in the last one. This is what I want. Okay, this is exactly how the problem read in the book, by the way. Calculate the delta H for this reaction. Here's the reaction that I'm shooting for at the end. Okay, these are the information that's given to me. Again, you maybe could have looked those up, but most of the time these are going to be given to you. And so then all I have to do is manipulate things. Okay, so again, this is what I'm shooting for down here in green. Just because I can, I'm going to go ahead and put my addition bar. Now, I'm not done with my manipulations yet. I left myself some room to do that. But that's just going to remind me that that's my goal, right, is that I'm trying to add things together to get to this green guy down here. Okay, so how do I get there? Well, obviously the first thing I want to do is that this C2H2 needs to be reversed, right, because I've got C2H2 as a product here. Okay, so fair enough. I'm going to move that up a little bit just to give me some space. And so I'm going to reverse that reaction. Okay, so I've got 2 CO2, okay, gas phase, plus H2O, liquid phase, okay, and then the other half is going to be C2H2, which is acetylene, by the way, but that's not particularly important to our problem, plus 5 halves O2. I know, fractions, it'll be alright though. Okay, so all I did was reverse that. Since I did reverse it, though, I'm going to change my sign. It was a negative. Now I'm going to make it positive. Okay, it's best to do that just right away, and then I'm just going to strike through this because I've already reversed it. I don't want to get myself confused. Okay, so that part's good. As far as the rest of the equation, I've got carbon on the correct side, and I've got hydrogen on the correct side, so that's good. But if you noticed here, what is going on here is I need 2 carbons, right? I mean, there's no way I can get to C2 unless I have 2 carbons. So that means that I'm going to take this equation and I'm going to multiply it by 2. And rather than, and again, don't let that panic you. Same thing we did in redox. I know that I need 2 at the end, so, or in redox we would have said I need to multiply it for the electrons. So in this case, I'm just going to multiply everything in it by 2, and that includes, by the way, the enthalpy. Okay, so I'm not going to rewrite the whole thing. Instead, I'm just going to go ahead and put this in front of it. So 2, okay, 2 and 2. All right, so hopefully everyone's all right with that. And then we're going to do the math here, and I'm going to cheat and actually look to make sure that I got the math right there. So negative 787. I know I'm lazy. I should have done it in my head. So negative 787.0 kilojoules. Okay. So now that I've done that, I'm going to cross this out to make sure I don't add it again because I changed it here. Okay, so negative 787.0 kilojoules. Now, what does that do to us as far as adding stuff up and canceling it out? Well, I bet we're probably there because I've got what I need, 2 carbons, 1 hydrogen, 1 acetylene, or 1 C2H2. And so now I just got to kind of hope that everything else cancels out the way I want it to cancel out. So let's look at it. I've got a liquid water here and a liquid water on the product side, right? Boom. That one's gone. And then here's the scary part, right? 5 halves oxygen. Oh my gosh, what the heck is that? Well, 5 halves oxygen, I've got 2 oxygen plus a half, right? 2 whole oxygens would be 4 halves plus 1 half. That's 5 halves. Boom. All of my oxygens are gone. So what am I left with? Carbon, 2 of them, right here. Hydrogen, H2 rather, sorry, right there. And then acetylene here. What else am I left with? Oh, 2 CO2s, right? But I've got another 2 CO2s up here, right? So boom, cancel that out. Now, everything's kosher. The only things I have left are acetylene, carbon, and hydrogen, so I'm golden. And now it's just a matter of doing the math here. So I added all of this up to get this, and so now I'm going to add all of this up to get my final answer, which would have been nice if I'd have typed it in, but apparently I got super lazy there and did not do that. So that's going to give us a delta H final, or total here, of, I know I'm cheating, 226.8 kilojoules. Okay, so as always, we're going to work some of these in class and work through some together, but I think this will give you a pretty good idea of how to work these. And of course, as always, if you need to, jump back and listen to it and rewatch it, and that will help you out. All right, thanks, guys.